friendos, it's MoNaCo here again.
And Milks?
I think we're on our 10th video. We're getting close to the end.
11 even.
Maybe.
We got one more after this.
Boom. So last video we were talking about polarity in simple molecules where there was two atoms covalently bonded together.
Yep. So now we're going to add a bunch more atoms together and make it a little bit bigger of a molecule.
Hopefully slowly, but yeah. Here we
Gotta
go.
add lots.
We got to look at the totality of the molecule
That's the idea.
and the directionality of these polar or nonpolar bonds and kind of pile it all together and do some mental vector math. That's
Right.
what Milks and I are doing. at
Yes.
least, to figure out if the molecule itself is polar or nonpolar, meaning does it pass the mirror test in 3 dimensions or does it fail the mirror
Right.
test in 3 dimensions?
Now, if you have no idea what we were just talking about, that's okay. We got some pictures that are going to help understand
Yes.
that. But before we even start, let's just make this blatantly clear. There is a difference between the polarity of a bond,
Correct?
and the polarity of the entire molecule.
Correct, because of reasons.
Because some bonds are going to cancel each other out. We'll find
Right.
directionality.
If the geometry of these molecules starts to play into that the polar bonds are opposing each other, then you'll see what happens, okay?
Well, this is exactly what we're talking about right here.
Okay.
So let's start with this first carbon dioxide first.
Cool.
All right.
O double bonded to C, double bonded to O.
Right. So what you're talking about with this vector math is, I have this
Dipole moment
going that way.
pointing that direction because oxygen is more electronegative than carbon, so it's going to pull the electrons to the side, the left side there.
Right.
Okay.
But I have another one on the other side pulling equal and opposite.
Oh, okay. So those two vector dipoles are equal and in opposite directions, so they will cancel each other out.
That's what I'm saying, and that's why we can jump right to the mirror test. Is it the same on both sides?
Yep.
And then cut it down this way. Is it the same on both sides?
Yep.
So it passes the mirror test very quickly because these cancel out. Now let's go over to carbon monoxide real quick.
Carbon monoxide. Okay, so carbon and oxygen are different elements. Oxygen pulls electrons stronger than carbon.
Right, and then here's that vector force that we were talking
The
about.
net dipole moment
And
is
there's nothing over here canceling
nothing
it out.
to cancel it out. So all the electrons are going to get pulled over to the oxygen side of that molecule, leaving carbon kind of bare and positive. And let's check the mirror
Right,
test.
so when I cut it,
Vertical, both sides don't match.
right, when I cut it this horizontal, it does.
It does, but
vertical
vertical fails. So that's what we're talking about, symmetrical, asymmetrical. So the asymmetrical, the ones that fail the mirror test, while they may have polar covalent bonds within them, in total, we've got a situation where our dipole moments cancel or compound each other.
Right.
And so
Now-
on the left-hand side, with the shape asymmetrical and symmetrical, we got some 4-dimensional ones.
Now
I'm sorry,
notice
three-dimensional.
both of these have that vector, but this hydrogen is different than that chlorine.
Right.
That's what ends up happening. So when I cut this one,
You're actually cutting it four different ways
right, you got to cut it many different ways to see
check-
how it is.
to check the
And it's going to be the same each time. So they all cancel each other out.
versus that one.
Versus the first one,
You cut it one way vertically and it passes, but as soon as you cut it another way,
you
it
got
fails.
hydrogen on one side and chlorine
Not
on the
on the
other. So now just the different kinds of atoms alone make it fail.
So this flow chart below each picture is really actually quite great because it shows you how you might have a polar bond in every scenario. You're starting with a polar bond.
But it doesn't mean you have a polar molecule.
Because the polarity directionality, the net dipole moments would cancel or not cancel, and the molecule results is polar or not polar. So when we simplify it to symmetrical equals nonpolar, unsymmetrical equals polar, we've already really kind of done due diligence to the whole polar bond, does the molecule cancel out, all that other stuff. So
Right.
we don't want to oversimplify this concept because it really is a lot deeper than just this.
Right, but at the same
surface
time,
area.
if you're a little bit not happy with us right now, we're not taking it as complex as we could because each one of these shapes has a name,
Linear,
And-
trigonal pyramidal,
and we're not going
trigonal
into that.
bipyramidal.
so we're not going into that.
Octahedral.
So
Yeah.
if you're mad at us, just remember we could take this a lot farther, and we're not.
Just
gonna.
remember, we could make geometry part of this unit if you
Yeah,
really
we
want
don't
to.
really want to. So let's just get through the notes for the unit for this
Yep.
part, right?
Symmetrical.
is going to equal,
Same on all sides.
which is going to equal,
Non-polar.
good.
Cool.
And then the exact opposite is true then for asymmetrical.
Different on Both sides?
Yeah,
Different
okay.
on one side. It
On
doesn't
at
really
least
matter.
one.
Yeah.
I mean, at least one is the way we should be phrased, right?
So one side is not like the others.
There you go. Which one of these things does not belong?
Polar.
And then that's polar.
Yeah.
So let's do the mirror test on these molecules real fast. First molecule, of course, is
CO2. Write the name down below. Carbon
Carbon
dioxide by our naming rules.
carbon dioxide. And I'm going to do these. We're going to cut them right,
I can
horizontal.
cut them. So the top and the bottom look pretty much the same to me.
Yep. And then
Left and right look the same to me. So I would say that's
Passes the mirror test.
So
symmetrical,
whoops. So this is
non-polar,
polar.
because it is symmetrical.
Right.
Okay.
All right, next one.
CH4.
Yep. We'll learn
Carbon-
that that's methane eventually.
Carbon tetrachloride's the
Tetra-
systematic.
Hy-
Yeah,
tetrahydride.
tetrahydride.
There you
My
go.
fault.
That's okay.
Carbon tetrahydride is the systematic name.
For
The
us.
common name is methane.
Correct. Let's see if it passes the test.
So I'm going to have to cut this in a
I'm
few
going to cut it
different
that way.
Left, top and bottom looks pretty similar to me. Yeah.
Yep, looks good. I cut it this way.
Left and right. Yeah.
So we're good. So this is
Non-polar.
Non-polar. It's the same on all sides.
I don't have a
Nice.
side that's obviously different.
I like that style. Oh, hydrogen chloride.
Hydrogen chloride. Before we learn how to call that methane, we'll learn how to call this hydrochloric acid.
Only when it's dissolved in water.
Oh yeah. Let's do the test though. So if I cut it this way, I
Pass.
same on both sides, and
Yeah.
then it's
Failed.
definitely chlorine on one side, hydrogen on the other. So now we
Failed
get
the mirror test means it's not symmetrical, which means that it is polar. That's a really easy one to see because that chlorine's so big.
right.
It's a hog for electrons.
Yep.
It's just totally lopsided
There you go.
molecule.
There's where things are going to get a little bit interesting.
Nitrogen trihydride, according to today's rules for
Yes.
naming.
Yep.
Common name ammonia.
Common name ammonia.
Let's pass that mirror test.
Okay, so as I cut across right off the bat,
Top and bottom wrong.
wrong. I got hydrogen on the bottom,
I got-
not on the top.
It looks to me like there's like almost 3 hydrogens on the bottom of this molecule.
Right, but they're not on the top, so now it's
Polar.
polar. And one of the tricks is when you're drawing these things, one of the tricks is if you see, well, let me do a different color.
Yeah.
If you see a lone pair of electrons on the central atom,
Yeah.
it's probably going to be polar.
Just
Just
one
a trick
lone
in that, any lone pairs.
Yeah.
Because this
usually
one's got,
typically-
next one's got 2.
Yeah. Okay, so let's see the name.
Next one is?
Dihydrogen monoxide. I heard this stuff's poisonous.
Aloe, as my little one used to call it when she was learning words.
Agua.
Yeah, agua, water.
Okay, that's the
So-
common name. That's not
Yep.
the system name.
So first time I cut
mirror
it,
test kind of passes. Top
passes.
and
I got
bottom.
hydrogen on
yeah.
either side, right?
Uh-huh.
Same angle, passes the mirror test that way, but not this way.
Wrong. Yeah.
So again, there would be 2
Two
lone pairs up here.
electrons if we were doing the Lewis dot structure.
Right, and then so that makes it very,
Asymmetrical,
which is
polar. Cool. Okay.
got
So at risk of teaching you the shortcut and not truly understanding, symmetrical, non-polar. Polar, asymmetrical. But remember the facts. You can have a polar bond within a molecule, like this CO2, that's CH4, but the molecule's geometry cancels all those dipole moments out.
right. You've got an equal kind of number of bonds in the same direction.
They're
So
all being pulled in the same direction. It's like 2 completely evenly matched tug-of-war.
so now we're not looking at just the bond between 2 atoms. We're looking at how they all interact.
molecules.
So that's the difference, guys, between a bond and a molecule. You got to pay attention to the words,
Yes.
attention to detail.
Yeah. You'll see this in Pogel.
Sure.
An actual 3-dimensional manipulative.
Right.
So polarity, to recap, polarity of molecules is different than polarity of bonds. You may have a polar bond, but a non-polar molecule. You always use electronegativity difference to figure this polarity out. And so then the basic breakdown is
Nonpolar equals symmetrical, which is same on all sides. Polar is asymmetrical, different on at least one side.
there you go.
Got
That's it. Thank you for watching.
One to go.
soup.